Hello, algebra. In this video, I'm going to cover the lesson on exponential functions. So you can see on the first page of the lesson, exponential functions follow this form. Y equals a times b to the x power. Anytime you have x in the exponent, that's what makes it an exponential function. B we refer to as the base. That's going to determine if you have growth or decay. And this a value is going to be your starting value or your y-intercept. So take a look at page 2. So an exponential function, the way that this is different than a linear function, the rate of change is not constant. So if you think of like the sequence 1, 2, 4, 8. 1, 2, 4, 8. I'm not increasing by the same rate each time. That'd be like plus 1, plus 2, plus 4. This would be an example of an exponential sequence or geometric sequence. Just to highlight this, the variable is in the exponent. So again, x is in the exponent. Any quantity that grows or decays by a fixed percent or rate at regular intervals is said to have exponential growth or exponential decay. So A, now you should be filling this out on your paper as we go along here. A is the y-intercept. And you can think of it as the initial value. And B is your rate or your base. So you're going to see how this ties into a geometric sequence right now. This was the explicit form for a geometric sequence. A sub 1, if you recall, was the first term, and R was your common ratio, what you were multiplying or dividing by. So what do you notice? These are similar. They're very similar. So what we can conclude from that is a geometric sequence is an exponential function. Geometric sequence is an exponential function. So if you need to pause the video to write this stuff down, make sure you're writing it down as I go along and work through this lesson with you. Please do that now. So you'll notice here, if we have exponential growth, we're adding the rate, 1 plus the rate. If we have exponential decay, we're doing 1 minus the rate. So if the situation is modeling growth, you're going to have a base or rate that is greater than 1. And if we're modeling decay, we're going to have a base or a rate that's between 0 and 1. Let me move that up for you. So growth is going to show a base or rate that's greater than 1, and decay is going to show a base or a rate that's between 0 and 1. If you have a negative number, that means something completely different, and a base of 1 wouldn't be growth or decay because when you multiply by 1, it doesn't change your value. Okay, so let's take a look at the next page. So in this example, it says, tell whether each of the following equations represents an exponential growth or decay. So what you need to do is look at the rate or the base. That's literally what you're looking at. So here is the rate or the base. 3 divided by 2 is equal to 1.5. Growth, that base or that rate is greater than 1. Decay, that rate or that base is between 0 and 1. So this would represent exponential growth. So what I'm going to ask you to do right now is pause the video in a moment and work through part B, C, D, and E. Just identifying are each of these exponential growth or decay by looking at the base. Go ahead and pause the video now and do that. Okay, hopefully you had a chance to work through those. Here, the base is 1.2. That's greater than 1. This represents exponential growth. Here, the base is 2. Again, greater than 1. This is exponential growth. The base is 1/4. This would represent exponential decay. And for E, the base or the rate is 0.5. That would also represent exponential decay. Here, the 1/4 is 0.25. So both of these bases or these rates are between 0 and 1, hence decay. All right. Looking at the middle section now, it says identify the initial value. That's your y-intercept, or think of like geometric sequences, kind of like the first term. The growth or decay factor, and the rate, the growth or decay rate. Okay, so growth or decay. So go ahead, pause the video in a moment. You should be able to answer these four that I just drew the arrow next to. Can you pause the video and see if you can do that for question 1 and question 2? All right, coming back here. Growth or decay, the base is 1.8. This is, oops, I'm sorry. The growth or decay, this is growth. This is decay because 0.8 is less than 1 but greater than 0. The initial value is 3. The initial value here is 9. The growth or decay factor, 1.8, 0.8. Now this decay rate, this is going to be something new. So I'm going to go back to the previous page. This is to find the rate. This is what I'm using to find the rate. Okay. So in this case, this was growth. So the growth rate, so 1.8 minus 1 is 0.8. So this is 0.8, or if I change it to a percentage, 80% growth. Here, I'm going to take to find the decay rate, 1 minus that base, 1 minus 0.8 is 0.2. So here the decay rate is 0.2 or 20%. All right, with that being modeled for you, I'd like you to work through question 3 and question 4. Pause the video now and do that. Okay, looking at question 3 and 4 now that you've done those. Question 3, this is going to be decay because that rate is less than 1 but greater than 0. The initial value is 2. The decay factor is 0.94. And the decay rate, 1 minus 0.94, is 0.06. So we're decaying at a rate of 6%, or 0.06. The second one, that rate is greater than 1, so this represents growth. The initial value is 2.1. The growth factor is 1.04, and the rate, 1.04 minus 1.04, so the rate is 0.04 or 4%. So you'll notice to find the actual rate, I'm taking the larger number minus the smaller number. So it's either 1 minus the decay rate or the growth rate minus 1. So that you always end up with a positive number. So if you're not sure, should I subtract from 1 or do the number minus 1, the bigger number minus the smaller number. All right, moving on to the next page in this lesson. So now we're going to write exponential functions. And the step 1 is converting that rate to the percent to a decimal by dividing by 100. So if I have 43%, I'm going to take 43 divided by 100, and this becomes 0.43. Essentially, I'm taking the decimal point and moving it 2 places to the left. If I have 5% and I move the decimal 2 places to the left, 0.05. So whether you use your calculator to do this or what I've shown you here, moving the decimal place, use one of those 2 strategies. Step 2, if the value is increasing, you're going to do 1 plus the rate. And if the value is decreasing, you're going to do 1 minus the rate. So some terms that you want to look for. Growth, grow, increasing, appreciate, accruing. Decreasing terms, depreciate, decline, diminish, decreasing, decaying. Those are kind of your keywords that you're going to look for to help you understand, is this exponential growth or is this exponential decay? So increase by 6%. So 6% as a decimal is 0.06. Increase, this is growth. So I would do 1 plus 0.06. Decreasing by 7.5%. Decreasing, that's decay. I'm going to change that 0.75. I'm sorry, that's 7.5% to a decimal. 0.075, it's decaying, so 1 minus. Can you work through these next two examples on your own? Pause the video and then come back and we'll go over them together. Accruing means like I'm getting more of, I'm increasing. So this is exponential growth. I changed the 2.5% to a decimal, 0.025, and this would be 1 plus. Diminishing is decreasing, decaying. So I changed that percent to a decimal, 0.067, and this is going to be 1 minus. So the reason that we went through that is now we're going to take a look at some word problems where you're going to have to figure that out on your own and make sense of how to actually come up with the equation. So here we go. A house that costs $200,000 will appreciate. A is typically going to go with an increase, an addition. So this is an increase in value by 3% each year. Write a function that models the cost of the house over time. Use X for years and Y for the value of the house in dollars. Okay, so I have to recognize this is exponential because it's increasing by 3% each year. So my form is Y equals A times B to the X. Now I just need to substitute in the initial value and the rate. So here, the initial value is the cost of the house, $200,000, times appreciate. It's increasing by 3%. So just like I did above, 1 plus 0.03 to the X. That's my function. Part B, find the value of the house at the end of 10 years. X is a number of years. So I'm just going to substitute in now X as 10. 10 years have passed. What is the value of this house? To the nearest dollar, it's $268,000. I'm sorry, $268,783. What would I do? I would literally just type this into my calculator as is, using the little caret for the exponent. If the house was purchased in 2001, what is the value of the house in 2019? So I need to find out how much time has passed between these 2 years. 18 years has passed. So I'm just evaluating my function after 18 years. Because it's increased at a rate of 3% per year for 18 years. At the end of those 18 years, this house is worth $340,487. Again, to the nearest dollar. I'm rounding to the nearest dollar, not cents, which you could do. Okay, so let's move on to another example. You have a bad cough and have to attend your little sister's choir concert. You take cough drops that contain 100 milligrams of menthol in each drop. Every minute, the amount of menthol in your body is cut in half. Write a function that models the amount of menthol in your body over time. X is minutes, Y is the amount of menthol. How do I know this is exponential? It doesn't have like a percent increase or decrease, but it really does because it's saying it's cut in half. If it's cut in half, that's a 50% decrease. So when I'm thinking about my exponential function here, the initial amount is the 100 milligrams times 1 minus 0.5. 50% is gone to the X. How much menthol is left in our body after 3 minutes? So this would be 100 times 1 minus 0.5 is just 0.5 to the third. After 3 minutes, there'd be 12.5 milligrams of the menthol left from the cough drop. This third part asks, is it safe to take a new cough drop after the level of menthol in your body is less than 5 milligrams? Or I'm sorry, it is safe once it's less than 5 milligrams. How long will it be before you can take another cough drop? So here's what I'm going to do. I'm going to take my calculator and I'm going to type this equation into y1. So I'm going to have to go to y equals on the calculator and type this equation in. And then I'm going to hit second graph. That's going to bring me to a table. And basically, I'm going to start scanning down the table. After 1 minute, there's 50 left. 2 minutes, 25. 3 is 12.5. 4 is 6.25. I'm running out of room. 5 is 3.125. So for us, after 5 minutes, that's how long I can wait. After 5 minutes, we can take another cough drop. All right, moving on to number 3. The most recent virus, I wonder what that is making people ill, is a fast multiplying one. Its growth is modeled by this function. Again, I know this is exponential because x is in the exponent. You should know if this is growth or decay already, and you should know what that 2 represents. X is the number of days, and V of x is the number of bugs present. So what we need to do, interpret the y-intercept. That's the initial value after 0 days. So this means there were 2 bugs present initially. Just a reminder, you should be writing all of this down as you go because you're going to need to use this lesson for the questions 1 through 5 on the quiz that you need to complete. Find the amount of bugs present on the 5th day. So this now becomes V of 5. X is the number of days. So 2 times 1.87 to the 5th. 46. Round your answer to the nearest whole number. So 46 bugs. Given the domain, state the range of the function. So the easiest way to do this is I go to my calculator, y equals, I type in this 2 times 1.87 to the caret x, and then I hit second graph, and I look at the table. And on the table, I should see 0, 1, 2, 3. I might need to hit the up and down arrow so that I can see those values. Range is y values. So when x is 0, y is 2. When x is 1, this is 4, 7, 13. I'm just rounding to the nearest whole number again. So the range would just be this set of data, 2, 4, 7, 13. So by the 4th day, there's 13 cases of this bug. All right, last page of the lesson, here goes. The depreciation of Ian's new Mercedes is modeled by this function. C of x equals 75,000 times 0.8 to the x. This is exponential because x is in the exponent. X is the number of years since he bought the car. Describe what C of x equals 38,400 means. This means the car's value after X years is $38,400. We don't know how many years have gone by, but after a certain number of years, the car is only worth $38,400, which is crazy because when he bought it, the initial cost was $75,000. So just a little side note here, cars lose a lot of value. Maybe not the best investment. Part B, describe what the 0.8 means. Well, this should tell you this is exponential decay. So 1 minus 0.8 is 0.2, or 20%. This means the car loses 20% of its value each year. And that's the reality of cars. They go down in price. as the years go by, unless it's some kind of collector car. So I hope that was a helpful introduction to exponential functions. You're going to need to use this lesson the week of February 1st to complete your quiz, because we don't have our traditional class. So if you do have any questions, reach out to myself or Mrs. Roan.